In this video, I am going to talk about maximum likelihood estimation through the example of estimating the bias of a coin. So we're going to try to figure out what the probability of heads is when we don't know it ahead of time. Of course, in this case, the underlying distribution is given in this probability table. We have probability of heads given by theta and probability of tails given by 1 minus theta. Okay? And so what we want to figure out is what theta is, and of course theta is some value between 0 and 1. And to figure this out, what we're going to have access to are n IID samples from the probability table for random variable x. Okay? Unlike previously in the class where we would write p of x or p of x dot to mean the probability table for x, now we're going to write p of x. We're going to have the parentheses as usual in the dot, but now we're also going to have this semicolon theta. And this notation means that everything after the semicolon is going to be what are called parameters. Okay? So in this case, there's only one parameter, the probability of heads. But in general, we could have many parameters that help us define what the underlying distribution is. So for example, when we looked at the binomial distribution, there were two parameters, the number of trials and also the probability of success per trial. And so for different distributions, you can have other kinds of parameters. But in this case, it's nice and simple. There's only one parameter, theta, for probability of heads. Okay? And note that often the n samples are referred to as training data. And we use this superscript notation to denote that, for example, this x superscript 1 is the first training data point, x superscript 2 is the second training data point, and so forth. And we put these parentheses to remind ourselves that we're not taking powers, okay? This is not x squared. This is the second training data point. And we don't use subscripts to denote which training data point it is because we'll reserve subscripts for the case when each training data point is actually a vector. And so then we're going to want to use the subscripts to index into the vector. All right, this is our setup. And as an example, if we see the sequence heads, tails, heads, this of course is the case when n, the number of samples or the number of training data, is 3. And so this thing here would be x1 and then x2 and then x3. Of course, the probability of seeing this is theta for the first heads, okay, times we see tails, so that's 1 minus theta, and then times heads, so probability of heads is theta, and we're multiplying them because they're independent. So this thing is, of course, theta squared times 1 minus theta, and this is the probability of seeing this sequence, right? So this is probability of x1, x2, x3 of heads, tails, heads, parametrized by theta. Okay? So we treat our observation as fixed. So this thing here is just a function of theta. Alright? So this thing here is called the likelihood. And it is the probability of seeing our training data given a specific choice of parameter or parameters. In this case, there's just one parameter. And so sometimes we'll denote this as capital L for likelihood of theta. Okay? The basic idea of maximum likelihood estimation is that to figure out theta, we're going to maximize this likelihood. We're going to say theta hat is equal to argmax over theta, and theta again is between 0 and 1 because it's a probability of this likelihood, L of theta. Okay? And so in this example we have, of course, argmax over theta within 0, 1 of theta squared times 1 minus theta. Alright. To maximize this, you might say something like, oh, I've seen things like this from calculus. I set the derivative with respect to theta of this thing to be equal to 0. And so you can do that. The main issue is that if we have many coin flips, when n is a very big number, and the number of heads and number of tails are also very big numbers, then we'll have theta to the power of number of heads, and 1 minus theta to the power of number of tails, and those are going to be such big numbers that if you try to use the product rule from calculus, then this is going to be very cumbersome to compute out, okay? A standard trick is to say that instead of maximizing this guy, we're going to take a order-preserving transformation of this where it doesn't change what the argmax is, okay? And a popular choice is to take the log. And in this case, I'm going to use natural log. So this thing is the same as the argmax of theta within 0, 1 of log of theta squared times 1 minus theta, okay? Because log is strictly monotonically increasing, okay? Log looks like this. This thing is going to be 2 log of theta plus log of 1 minus theta. Again, these are natural logs. And to maximize this thing, I can now take the derivative with respect to theta and set it equal to 0. Okay, and if I take the derivative, I get 2 over theta plus 1 over 1 minus theta, and then times minus 1. Remember the chain rule? We have this minus theta, so now that's minus 1 here. I'm just going to write this as minus, okay, like that. And so I'm going to set this derivative equal to 0. And what that amounts to is 2 over theta equals 1 over 1 minus theta. So 2 times 1 minus theta is equal to theta. So 2 minus 2 theta equals theta. 2 equals 3 theta. So the best choice is theta hat is equal to 2/3. So at this point, to actually show that this is the maximum, you would need to look at the second derivative test. So you would take the derivative of this first derivative, all right, and you would evaluate the second derivative at 2/3, okay, and check if it's a negative number to see if this is a local maximum. All right, and then you would also need to check the endpoint, okay? You would check what the log likelihood evaluates to at 0 and 1 and see how those values compare with the log likelihood evaluated at 2/3, okay? So I'll show that in the general case very shortly when we talk about when we have n coin flips, but for now I'll just say that if you show those specific things, you'll find that indeed this is the maximum likelihood estimate given this particular sequence, heads, tails, heads. Okay? This 2/3 should hopefully be intuitive. If we're given the sequence heads, tails, heads, and that's all we had to work off of to figure out the probability of heads, well, a natural thing to do is to look at the fraction of heads, right? So, which is 2/3. All right? So note that if we had instead seen heads, heads, tails, we would have the exact same likelihood of theta squared times 1 minus theta. Okay, so the ordering of these training data points doesn't actually matter. We would still get the same maximum likelihood estimate. Now I'm going to show the general case where we have n coin flips. And the result is not going to be surprising. The result is going to be, well, theta hat is just going to be the fraction of heads. So the main thing is working out the details so that you can see clearly why that's actually the case. So in general, the likelihood p of x1 up through xn of little x1 up through little xn, so this distribution parametrized by theta is going to be equal to, well, because of independence, this is going to be the product from I equals 1 to n of this probability table px that we've been working with, evaluated at little x superscript I, so the ith training data point, this distribution parametrized by theta. And as we saw, the ordering of these doesn't actually matter, and this thing is just going to end up being equal to theta to the power of, I'll now introduce n sub h to mean the number of heads, times 1 minus theta to the power of number of tails, which I denote by n sub t. So nh, the number of heads, is of course given by I sum from I equals 1 to n of indicator function of whether the ith training data point is equal to heads. And then of course the number of tails is very similar. I'm going to sum over all the training data points and look at the indicator function for whether the ith training data point is equal to tails. Of course, a different way to do this would be to just say, well, this is just n minus the number of heads. So this thing here is a likelihood. Again, this, once we treat the training data as fixed, this is just a function of theta. So L of theta. And commonly, when we talk about the log likelihood, people use the notation little l of theta to be log of big L of theta, so the log likelihood. All right, and this is, of course, going to be equal to number of heads times log of theta. Again, these are natural logs, plus number of tails times log of 1 minus theta. And now we're going to maximize this log likelihood. And so now I'm going to take the derivative with respect to theta. All right, and then we're going to be setting that equal to 0. So dl over d theta of theta is going to be equal to number of heads divided by theta plus number of tails divided by 1 minus theta times the minus 1 because of the chain rule, which I will write here as before. So note that this derivative here isn't actually defined for when theta is 0 or when theta is equal to 1. To be careful here, I'm going to break up the analysis into 3 cases, and we're going to get the outcome that we expect, that the maximum likelihood estimate here is the same thing in all 3 cases, as in it's just going to be a fraction of heads. So in the first case, we're going to consider a simple situation where the number of heads is equal to 0 and the number of tails is bigger than 0. All right? Of course, if they're both equal to 0, that's not very interesting because that means that we didn't observe anything, and so we don't have anything to work off of. Right? So we're not going to consider that case. We're going to assume that we have at least one observation. So in this particular case, the log likelihood, L of theta, is going to just be equal to this. So the first term is 0, and the second term is going to be n. So n and nt are going to be the same in this case because we only have tails. So we're going to have n times log of 1 minus theta. All right? So log of 1 minus theta increases as 1 minus theta increases. All right? Which means that it increases when theta decreases. So what that means is that to make the log likelihood as large as possible in this case, we want to make theta as small as possible. And the smallest theta can be is 0. Remember that theta is between 0 and 1. Alright, so the best choice here is theta hat equals 0. Again, log of 1 minus theta increases when 1 minus theta increases, which happens when theta decreases. So lower theta means the log likelihood is going to be higher, and the lowest we can set theta is 0. And of course, this is equal to the fraction of heads because the number of heads is 0. So this is going to be equal to 0 divided by the total number of tosses. Alright, so now we're going to look at case 2, which is when the number of heads is greater than 0, the number of tails is equal to 0. In this case, the log likelihood is going to be equal to, well, the second term is 0 because nt is 0, and the first term is just going to be n, since the number of heads is equal to n in this case when we don't have tails. So we have n times log of theta. Alright, and so as a function of theta, to make this as big as possible, we want theta to be as big as possible, which of course is when theta hat is set to be equal to 1. This of course is equal to the fraction of heads because we have no tails. Alright, so this is going to be equal to nh, which in this case is equal to n, divided by n. Alright, so again, this is the fraction of heads. Finally, we look at case 3 when the number of heads is greater than 0 and the number of tails is greater than 0. And now we're going to return to looking at this derivative. So the issue before that I mentioned was that the derivative isn't actually defined when theta is equal to 0 or when theta is equal to 1. For this third case here, when we set this derivative equal to 0, the best choice of theta will actually never equal 0 or 1. So we're not going to run into this, what happens if we divide by 0. So in this case, we set the derivative equal to 0, so nh divided by theta minus nt divided by 1 minus theta equals 0. And this is, of course, same as saying number of heads divided by theta is equal to number of tails divided by 1 minus theta. And so we have number of heads times 1 minus theta equals number of tails times theta, which we can write as number of heads minus number of heads times theta equals number of tails times theta. So number of heads is equal to number of heads plus number of tails times theta. So this, of course, is n. And so this means that theta hat is equal to number of heads divided by n. And so in particular, theta hat in this case is going to be strictly greater than 0 and less than 1, because we have assumed that there's at least 1 of heads and 1 of tails, so we don't run into the issue of evaluating the derivative at a point where it is actually not defined. Good. So again, we get theta hat is the fraction of heads. Okay, but we're not done here, because earlier in these two examples I justified why this is actually the argmax for these two expressions. Here, to justify why this is the argmax, we look at the second derivative. So we take the derivative here, and we now look at the second derivative, d squared of L over d theta squared of theta, which is going to be equal to minus nh over theta squared, and then it's going to be, let me move everything down a little bit. So we have this, and then we have plus nt divided by 1 minus theta squared times, because of the chain rule, a minus 1, which means that this is equal to minus of this thing. And so note that when we plug in any theta that is between 0 and 1, not equal to 0 and not equal to 1, so that this is actually a real number, okay, so we have a positive number divided by a positive number divided by a positive number, so this thing is always going to be a negative number. And so this thing evaluated at theta hat is certainly going to be negative, which means that this is indeed a local maximum. So finally, we evaluate the log likelihood at the boundary points L of 0 and L of 1, and also L of theta hat. So what are these equal to? Here we have number of heads times log of 0 plus number of tails times log of 1. So this is 0, and this thing is going to be going to minus infinity. Alright, so what about L of 1? Well, this is number of heads times log of 1 plus number of tails times log of 1 minus 1, so 0. Alright, so now this thing goes to 0, and this thing goes to minus infinity. And now what about the log likelihood evaluated at theta hat? Well, we're going to have number of heads times log of the number of heads divided by n plus number of tails times log of 1 minus this thing, which is of course the number of tails divided by n. So this thing, well, for sure these quantities aren't exploding to minus infinity. They're going to be negative numbers, but not minus infinity. So actually none of these quantities are going to minus infinity. So we know that this is greater than minus infinity, okay? It's definitely higher than these two values. What this means is that we did the second derivative test to make sure that this thing here is a local maximum, and then we checked the boundaries and saw that indeed, not only is this a local maximum, it is the unique maximum. So the result for all three cases is the same and can be summarized by this formula right here. So the maximum likelihood estimate theta hat for parameter theta is given by the fraction of heads that we see in the training data.